So, good afternoon and welcome everyone. My name is Sonia Collier and I am a staff air pollution specialist working in CARB's research program. This is the final seminar for the project titled Low Carbon Transportation Incentive Strategies Using Performance Evaluation Tools for Heavy Duty Trucks and Off-Road Equipment. It's also known as CARB contract number 19RD026. So this contract is almost complete. A draft final report was reviewed by CARB's Research Screening Committee earlier this year, and they provided recommendations to the research team. This seminar is being recorded and will be posted on the contract page hosted by CARB's website. And I'm going to post a link to that contract page now. Let me find this chat window. Here we go. Everyone in the meeting. All right. All right, so the link for CARB's contract page for this contract is now in the chat. So you can check on that maybe like in a couple of weeks to see the meeting recording, the slides, etc. Yeah, so the slides and final report will also be posted on that same site once they are finalized and made ADA compliant. Please be patient with us as we work to create accessible versions of those documents. It is a time-consuming but required and mandated process. So I will start by giving a brief introduction to this topic, and then I will hand it over to Dr. Craig Rent to begin the presentation. I invite all participants to use the chat to introduce yourselves and to post your questions throughout the presentation. So we will not be answering questions during the presentation. We will be answering questions at the end. However, the research team, anyone on the research team that's not actively presenting might answer some of your questions during the presentation, but in the chat. So I will help facilitate the question and answer session at the end by calling on participants who want to ask verbal questions using the raised hand feature, or by reading your questions submitted through the chat if there's any that remain unanswered. So the transportation, so I'm going to start. We're going to start the introduction part now. The transportation sector is California's largest emitter of oxides of nitrogen and greenhouse gases, and off-road equipment is one of the largest sources, or now the largest source, of NOx emissions statewide. So to meet federal health-based air quality standards and California climate change goals, medium and heavy-duty trucks and off-road equipment operating in California must transition to low NOx emission technologies coupled with advanced renewable fuels and to zero-emission vehicles where possible. So to that end, CARB has various regulatory programs aimed at reducing greenhouse gas emissions as well as toxic air pollutant emissions. California regulations for heavy-duty vehicles include the truck and bus regulation, the heavy-duty tractor-trailer greenhouse gas regulation, and the drayage regulation, which are expected to help reduce heavy-duty vehicle NOx emissions by 2031. CARB also manages incentive programs to induce purchases of low-carbon trucks and off-road equipment and accelerate replacement or scrappage of high-emitting vehicles, such as the Hybrid and Zero-Emission Truck and Bus Voucher Incentive Project, or HVIP, Carl Morrill Program, the Clean Off-Road Equipment, or CORE Voucher Incentive Project, Agricultural Replacement Measures for Emission Reductions, or FARMER Program, and others. Also, the Low Carbon Fuel Standard, which sets annual carbon intensity standards or benchmarks for gasoline, diesel, and the fuels that replace them, induces the transportation sector to adopt lower intensity carbon fuel more widely in the state. Incentive programs need to be designed effectively to promote clean technology uptake and nudge the market to transform permanently. But in order to design incentive programs or regulations that will move heavy-duty vehicles and off-road equipment sectors towards a cleaner and more sustainable future, a comprehensive analysis of market survey and vehicle operation data is needed to understand the most effective methods to incentivize low-carbon technologies. The objective of this project is to identify potential policy and incentive strategies that promote greater adoption of low-carbon transportation technologies. So that includes zero and near zero emissions in the heavy-duty and off-road sectors. To that end, CARB awarded a contract to Professor Stephen Ritchie of the University of California, Irvine. Professor Ritchie put together a multidisciplinary team of experts from UC Los Angeles, UC Riverside, and University of Arkansas. So next, I will be turning it over to Dr. Craig Rind, who is the project manager for this contract. So Dr. Craig Rind is the Assistant Director for Research Coordination at the Institute of Transportation Studies at the University of California, Irvine, where he has been a project scientist since being awarded a PhD in civil and environmental engineering for his work in travel behavior modeling and transportation systems management using intelligent transportation systems technology. Dr. Rind's recent research has focused on freight operations with a particular emphasis on the use of alternative fuel vehicles in the heavy-duty vehicle sector. So Dr. Rind, I'll hand it over to you to begin the presentation.
Great, thanks so much, Sonia, and thanks everyone for joining us this afternoon. We're pleased to be presenting the results of this project to you, but we do have a lot to cover, so I'm just going to jump right in. So let me start with a quick overview of the project team. Sonia's already done this largely, but I want to tip my cap to everybody. So we have had contributions from a lot of people at UCI Institute of Transportation Studies. Again, Professor Stephen Ritchie is the PI. I'm the project scientist that served as project manager. We also had contributions from Dr. Young-Eun Bae and Dr. Andre Tok, as well as Dr. Nyla Sharmin early in the project. And Minky Yao was a graduate student researcher who contributed to our analysis of incentives. At the Advanced Power and Energy Program, Professor Scott Samuelson was co-PI on the project. And his staff scientists, Dr. Blake Lane, Dr. Kate Forrest, and Dr. Mike McKinnon all contributed. I just will note the people in blue in this chart are presenting today, just to call them out. At UCLA, Dr. Bo Liu, who's now with NREL, was an important part of the team, and we'll get into the design of the performance evaluation tool, just kind of Bo's baby. Early on in the project, James DiFilippo, who's now with Atlas Public Policy, also contributed. At UC Riverside, we had co-PI Dr. Canuck Borabunson. Sorry, Canuck, I always trip up there. And now Dr. Fuad Unnur, who was a GSR on this project earlier on. At University of Arkansas, we have Professor Suman Mitra and his graduate students Farzana Tuli and Bhuban Chowdhury, who contributed. Let's see, moving on. So project objectives, I think Sonia did a great job here. Our work focused on developing a tool to understand how regulatory measures and incentive programs can affect the market. And the research used that tool to project the uptake of technology for low carbon transportation. We looked at various policy actions to improve and optimize the energy demands of both heavy duty vehicles and off-road equipment under various operational and market conditions. So this work was structured around 4 general stages. One was the kind of assessing current programs, and that was both incentive programs and regulatory programs. Then we moved into, some of this happened simultaneously, but we also did a technology and market assessment, a sort of a supply side assessment of heavy duty equipment, off-road equipment, and fuel technologies, as well as behavioral characteristics of the decision makers who drive the transition at the fleet level. Those fed into the performance evaluation tool that's kind of at the heart of this work. That we developed and then used to provide recommended strategies for incentivization in the face of a variety of regulatory policy and market scenarios. So really quickly, just an overview and sort of an agenda of the presentation today. There's kind of 5 areas. The first is that incentive and regulatory program and market analysis. The second is the transition to low carbon technology. Again, that's sort of a supply side look. And Blake Lane is going to jump in here and talk about the trace model that kind of that was sort of the underpinning of our technology and fuel forecasts for this project. Then I'll hand it off to Suman Mitra, who will discuss the behavioral factors that we just talked about and some structured interviews and the findings that we got from those. Those 3 things fed into that performance evaluation tool I mentioned. I'll be talking about that today. Dr. Liu is unavailable to present, but he is available for questions at the end. And then I'll also talk about sort of the model sensitivity and the strategy development at the end. Okay, so we began with a review of existing and planned incentive and regulatory programs to understand what should be included in our model. And so while this work originally targeted the policies surrounding, in this figure here, the technology readiness levels 7 through 9, those are designed to foster the low carbon technologies from the pre-commercial through the market scale deployment. The primary focus really in this work was understanding and representing the sort of market scale, the TRL 9 policies. There are that sort of right side of that arrow on the top there. I guess I have a little pointer here. So to do this, we sought data on the programs linked in red. So these arrows kind of link across here. And if you go over here, you can see that they cover sort of broad purchase and fleet turnover incentives. That includes CARB's sort of main funding mechanisms through CORE and HVIP, as well as others in these categories that Sonia outlined just a minute ago. And then we also look to identify current and pending applicable regulations to include in that PET model. So we started with identifying sort of the core features of incentive programs with an initial focus on the heavy duty vehicle side. So the main policy mechanisms you can see in this table here include the reduction of capital costs of heavy duty and off-road equipment, reducing the capital costs of the installation of refueling equipment, as well as reductions in the cost of fuel. So right now, we mainly focus on the first two, that is reducing the capital costs of vehicles and equipment. In the next section, we'll talk a little bit how we treated fuel subsidies in the TRACE model. So from our review, we identified a number of features of these programs to represent in the PET, and that includes the incentive amounts that are available, which may vary by fleet characteristics, various eligibility requirements, vocational targets, the size, whether they're public or private, scrappage requirements, as well as other limits, including things like maximum amounts available from the program, whether or not incentives can be stacked from particular programs, and the total funding available. Also, whether or not there's a time frame for the program and just the general structure of the incentives. So we looked at a range of incentive programs to identify those salient features. I think Sonia already kind of talked about most of the ones that we looked at, but there's the HVIP program, as well as Carl Moyer. General distinctions between these. HVIP are, they're market transformation. It's a market transformation program targeting zero emission trucks and buses in California. It started in 2009. And as of May 23, and I know this has probably changed, about $1 billion in funding had been allocated, with about 300 million of that implemented to that date. That program keeps evolving. There are vocation-specific set-asides as well as adjustments for fleet sizes, all of which are relevant and important to the development of the PET. Carl Moyer is another option. I can't go through all of these in detail. It's grant funding for cleaner than required engines, equipment, and other sources of pollution. And that's implemented as a partnership.
Appreciate it. Thank you.
I'm hearing somebody talk there, sorry. Additional programs that we looked at were the VW settlement. And when I say we looked at the structure of the program. We also got data from CARB on these, on incentives spent, or incentive dollars allocated, and vehicles and equipment purchased. There's also the Prop 1B goods movement and emission reduction program that we looked at and got data on. All of these targeting heavy duty trucks that were the focus. For off-road equipment, we looked at the following: the CORE program and the farmer program that Sonia mentioned, as well as the surplus off-road opt-in for NOx program. As well as, and Carl Moyer applies there, as well as local programs. We also considered infrastructure incentives. The big one there is CEC's Energize program that has 4 different lanes. for EVs, specifically for public charging as well as for hydrogen refueling. Generally speaking, we consider these to be agnostic, whether, with respect to heavy-duty vehicles versus off-road equipment, and they'd be applicable for both. But infrastructure costs we know are critical to the total cost of ownership, which for heavy-duty or for all-fuel vehicles, which is going to be the center of what we talk about. We also identified infrastructure incentives provided by California's utilities. We looked at sort of the utility level commercial both charging, and they actually do have some vehicle incentives as well for the major utilities in California. We looked at Burbank, Glendale, LADWP, Pacific Gas and Electric, Southern California Edison, SDG&E, as well as Sacramento Municipal. And this chart shows sort of the range of incentives that we identified. Most of them on this chart are for different levels of charging, incentives for different levels of charging. In our model, we focused on the highest levels here, which are the ones that are marked by the X in the chart. But so anyway, we collected this data and adapted it for use in our model. In addition to the incentives, there are regulatory programs that are important to modeling how fleets will transition over time. We only looked at regulatory programs that were going to be impacting our target model horizon, which is 2020 to 2050. So the first was the truck and bus rule, which, though it's almost completely implemented, our model goes from 2020 to 2050, and there are some characteristics, or there are some compliance deadlines from 2021 to 2023 that were specified in the truck and bus rule that required certain model years to be retired from the fleet in those years. So we wanted to represent that. A second regulatory program we looked at was the Advanced Clean Trucks program, which was approved in 2019. That is a manufacturer ZEV sales requirement, essentially a supply side target. Because the model that we've developed, the PET model, it's primarily a demand side model. It's very difficult to represent supply side targets. We aren't modeling OEMs directly in our model, so we weren't able to represent the impact of advanced clean fleets directly in the PET. Advanced clean trucks. Advanced clean fleets is a different story. The salient features of advanced clean fleets, which was approved last year, are the manufacturer sales mandate, which is that OEMs can only sell zero-emission medium and heavy-duty vehicles in California starting in 2036. But then on top of that, there's the drayage fleet rule. Starting in 2024, any new drayage trucks placed into service must be zero-emission, and all drayage trucks must be zero-emission by 2035. There's also a state and local agency requirement on there, as well as the high priority, let's call it high priority, I'm going to call it the large fleet and federal fleets rule that implements two options. One is a model year schedule that basically says from 2024, they can only purchase zero-emission vehicles for their heavy-duty fleets. And I say from 2024, but I think it's from 2027, they have to remove ICE vehicles at the end of their useful life, and it may be 2024. The other option is a ZEV milestones option, which states that they have to hit a percentage of vehicles within their fleet have to hit these targets. I'll get into this a little bit later. We can't model directly the ZEV milestones because we don't model fleets, and we can't model the state and local agencies, or we don't, because we don't consider that particular type in our modeling, the MFAC class in our modeling, so it wasn't relevant. But we do model the drayage, high priority, and sales mandates in our work. Similarly, we looked at the off-road equipment regulatory programs. Now, we know that CARB has more limited regulatory authority for off-road equipment, in part due to complications related to federal preemption. So that smaller equipment is difficult for CARB to regulate. Nonetheless, we identified the regulations shown here to consider and recognize that CARB is looking for support in developing some new regulations. So we're hopeful that our work can help that. And then critical to our later analysis was the ability to assess the performance of incentive programs so we reviewed the literature to identify useful metrics for this work. And we settled on a cost effectiveness analysis used by the CMAQ program, which is shown here to assess the relative cost benefit of particular programs. That's primarily in this table. It's kind of targeting, I guess, the second thing, emission reduction and health benefits. But we also consider market penetration in our uptake forecasts later on. But because this work is primarily a demand side analysis, it's difficult for us to consider that third one, the technology evolution and viability directly in the model, but we do consider it in scenarios. So we did try to assess the performance of prior programs using data from the programs shown here, but we found that the data wasn't sufficient at this time for a causal analysis because the way the programs were implemented did not include sufficient variation. And we agreed with CARB staff that going forward, program managers should coordinate with behavioral economists at CARB to specifically target causal effects as they design programs. With that, we'll now turn to our work focusing on the transition to low carbon transportation technologies. This part of the research focused on establishing baseline vehicle equipment and fuel costs for 2020 and forecasting them out to 2050. So my colleague, Blake Lane, will be presenting this work. Dr. Lane is a senior scientist at the Advanced Power and Energy Program at UCI, where he manages the vehicle and fuel research operations. After receiving a PhD in mechanical and aerospace engineering for work on the optimal rollout of alternative vehicle and fuel technologies, which is used in this research. Dr. Lane's research currently focuses on techno-economic and market projections for alternative powertrains and fuels, as well as energy impacts of cooperative driving automation for zero-emission vehicles. Blake?
Thank you, Craig. All right, I'm going to run through this pretty quickly because these are really the inputs that are mostly used by PET, or also to set up kind of a target, if you will, for some of the outcomes. So this slide here just shows something that I think we all know is zero-emission vehicle powertrains are improving quite dramatically in recent years, to the extent that these were our main focus in this project to reduce the carbon footprint of transportation. And so what we see here is for a variety of different vocations, truck configurations, et cetera, we have a range for both battery and fuel cell electric powertrains that is sufficient for not necessarily every single application, but the majority of applications, if not today, in the very near future. And so these things, including the range, the fueling time, et cetera, for both of these zero-emission technologies, enable us to focus on those for deployment. So on the next slide, to talk about exactly what we modeled in the rollout of vehicles. Again, both battery and fuel cell electric vehicles were considered, both of them being zero-emission technologies with different applications potentially for each of these, different weightings in the rollout, as we will see. However, while focusing on zero-emission vehicles, we also included analysis for internal combustion vehicles, both diesel and compressed natural gas, as well as the renewable counterparts of these. So the engines and powertrain being essentially the same, but the fuel being put into them being different, particularly in terms of the carbon footprint. As Craig has mentioned, we pulled heavily from MFAC for the vocations that we modeled, and these were focused on primarily for drayage, line haul, and for better or worse, MFAC does not really include a lot of detail on what's exactly included in line haul. So there's both short and long haul within that category there. And then also on-road construction vehicles. So these are selected mostly in terms of their impact on the fuel requirement, on the emissions that were coming out of these vehicles, as well as the convenience, if you will, of the duty cycles on the whole for adopting these zero emission technologies in the shorter term. And so we laid out a baseline of cost that you can see on the right there for the different components, the powertrain components, assuming the glider was essentially the same between these different powertrain configurations. And then from there, we'll get into how we projected these. So TRACE is an acronym, Transportation Rollout Affecting Costs and Emissions. This is an optimization tool that we developed and particularly in this project, fine-tuned and updated with techno-economic data for application in the kind of the more recent costs of the technologies, as well as some of the important goals that we have for environmental constraints, ultimately, as they were put in here. So this was initially developed under a different CARB project a few years back. And some aspects here that were important were the fact that we have different vocations modeled, as we just covered from MFAC, and we project out to 2050. We cover the fuel projections from feedstock all the way through the distribution and dispensing of the fuels. So we're looking at the emissions as well as the costs of these different 40-some fuel pathways that we've modeled, as well as noted in the last slide, the different powertrain components and glider for the vehicles. For both of these fuel and vehicle technologies, we use Wright's Law, which we'll get into in a little bit more detail. And we also model just a couple of the incentive programs, particularly on the fuel side, low carbon fuel standard, as well as renewable fuel standard from the federal side. On the right, you see a diagram, essentially techno-economic analysis being done from literature as a key input, as well as emissions inventories coming out with a suggested deployment of these zero emission tools from a supply side perspective. Another important aspect is the availability of these different fuels, and this is really key for particularly the different types of bio-derived fuels, as well as understanding what is the impact of producing electrolytic fuels, specifically electrolytic hydrogen, as well as direct fueling of battery electric vehicles through electric vehicle chargers. So we looked primarily at E3 pathways, as well as the DOE's billion-ton report for the electricity and biomass availabilities respectively, and incorporated these as constraints to determine to what extent different types of fuel pathways could be utilized to come up with ultimately the projected vehicle deployment by powertrain. So to get into a little bit more about how we projected costs, again, using Wright's Law. And so you might be more familiar with Moore's Law, which suggests technologies become cheaper with time as the technology is developed. This is very much akin to that, but instead of time being the x-axis, if you will, really it's the production quantity that enables the reduction in cost. And so we applied Wright's Law, and you can see a couple examples in the plot on the right, to the different fuel production technologies to project out the electricity costs at the various charging levels, the hydrogen costs with a couple of different categories, again, electrolytic or biomass, renewable natural gas, and renewable diesel with various production pathways and feedstocks therein. So you can see there's kind of a baseline, if you will, of costs that we use kind of downstream, but also in some cases a pretty wide gap in terms of uncertainty. And that uncertainty we'll talk a little bit about more shortly. But a couple of the key factors that lead to that is the quantity of the technology deployed. And this is not something that's heavy duty vehicle specific. This is something that is economy wide, right? So hydrogen is not looked at just for heavy duty vehicles. So other sectors of the economy can have an impact on the cost of the fuel for heavy duty vehicles. And then there's also the learning rate. So for a given increase in capacity that's made, how much of a percentage reduction in cost is there? So we played with a couple of these variables. And on the next slide, I believe, we have where we really focused on this playing, if you will, using a Monte Carlo simulation for the hydrogen specifically. The reason we focused, we did this analysis on hydrogen there's quite a lot of uncertainty in terms of electrolytic versus biomass hydrogen. Today, as we know, most of the hydrogen is produced from fossil fuels. But looking into the future, we're expecting a combination of electrolytic and biomass to make hydrogen. But there's a variety of different factors in terms of the cost today, the cost tomorrow, the cost over the coming decades. And we modeled that uncertainty with the feedstock costs, with the technologies used to make hydrogen, and then the learning rate as well. So from that, we put all these inputs in, cost inputs, constraints from things like MFAC and other emission factors and regulations that we modeled in terms of economic and environmental goals, and came out with kind of the main, if you will, output of TRACE, which is what we see in the bottom there, deployments, optimal deployments from the supply side for the different powertrain technologies. And so with that, I think that leads into the last slide that I'll be, sorry. So the handoff there is really just to use that as a target for what the PET tool can come up with in terms of from the demand side. So sorry, hand it back to you, Craig.
Thanks, Blake. Jump forward here. Here we go. So next we'll turn to our work focusing on the demand side behavioral factors that impact the uptake of LCT technology. Apologies for this slide. I know it's a kind of an overly detailed picture, but it's just to give you I don't know, a 40,000-foot view of our behavioral work that started from a framework, this framework that Dr. Young-In Bae developed for characterizing organizational decision-making related to fleet adoption of alt-fuel vehicles. The diagram, I can summarize it pretty quickly for you. It shows the complex relationships between the various factors influencing decision-making, including sort of the basic fleet characteristics, such as the sector vocation, fleet size, the location of the fleet, operational characteristics, which are tied to the vocation, as well as a fleet's prior experiences with alternative fuel vehicles. External factors, including supplier efforts, government policy, incentives, as well as social influences, characteristics of the organization, including things like business strategy and their values, as well as technology characteristics that are kind of split into sort of monetary and non-monetary factors. So this framework hasn't yet been quantitatively validated, although Dr. Bae has recently collected data from a choice experiment with fleets in California and is working on finishing a model based upon that data and based upon this qualitative framework. For this project, we use this framework as the underpinning for a qualitative research design that my colleague, Dr. Mitra, will cover next. So let me give him a brief introduction. Dr. Mitra is an assistant professor in the Department of Civil Engineering at the University of Arkansas, Fayetteville. His primary research interests include travel behavior analysis of special population groups, sustainable transportation, and emerging transportation technologies. Dr. Mitra's current research focuses on how technological advances in transportation can best serve the disadvantaged population through the integration of transportation systems, economic activities, and land uses. Shuman?
Yes. Good afternoon, everyone. Thank you, Craig. So as Craig mentioned, that objective of this part of the research was to understand the adoption of low carbon transportation in heavy duty and off-road sectors. And we have some specific research questions we handled in this part of the project. That we want to know what are the heavy duty vehicles perception and knowledge about low carbon vehicles. And when I'm mentioning heavy duty vehicles, I also included off-road equipment sectors into that. I did not write it here. And the second objective was to what are the motivators or barriers for low carbon adoption. And then we also want to look into the incentives role, because there are lots going on the incentive side, but we really don't have an understanding on the roles of the incentives in the adoption behavior of the low carbon. And also we want to know that what is the perception and knowledge about these incentives among those adopters or the non-adopters. The methodology we use the semi-structured interview. This is a more qualitative study. As Craig mentioned, the framework we developed initially, that was also based on qualitative, but this is Specifically, our target group was some small fleets. We target both, but our main group was small fleets. There's a gap on that. And we believe that through the qualitative study, we can get more in-depth understanding, which through the quantitative model, sometimes we miss. So we try to collect data through semi-structured interview, and we use the method called content analysis. I'm not going into detail on that, but those are the methods we used for this analysis. Now let's talk about the semi-structured interview a little bit. That's how we did that. Next slide, Craig. So we actually applied the purposive sampling methods, and we actually contacted thousands of companies. We had the list of like 74 on-road we collected from online, then off-road 56. The off-road, this list we got from UC Riverside, they worked before, and also from online we got. And we also have race companies, which has 1945 contacts. And we contacted them. The way we contacted, different methods we applied. Next slide, Craig. We actually called them. We made more than 400 calls, and then we emailed them. Through the LinkedIn, we contacted them. And after doing all those things from few months, we only got actually 12 response who agreed actually. Initially, 15 or maybe more than 15, around 20 agreed, but at the end, only 12 participated. And among those 12, 8 is on-road and 4 is off-road. And also one thing I did not mention here, that among these 12, actually, 8 are actually from a smaller fleet and 4 is from that's larger fleet size. And there are other characteristics you can see from here. I'm not going into detail about that, but there are 7 non-race and 1 race things companies. Now let's talk about the content analysis, how we analyze this data. Next slide, Craig. So say we have the main research question. First one is, what are the motivators or barriers? And based on these research questions, we developed a coding framework. And in that coding framework, for this specific research question, we'll be using the barriers to LCT adoption. Then we have the second and third category of coding or some specific characteristics. And based on those characteristics, we looked into the survey we did, and we go through those, and or mainly the transcription we read, and then we come up with some codes which actually represent those categories. And based on those codes, then we have the coder. We generally use 3 coders, and we actually give some points. Like this could be based on their impression or based on their importance. We give them some points, and based on the points, we have some value for each category. And that's I'm going to analyze in the next slides. So the first one, we want to know what is the awareness and impression of the low carbon vehicles. The first one is the awareness scale. As I mentioned, we have 3 coders based on the codes. This is the average value we are showing. This is not the detailed one. In the report, we provide the detail, but this is the average value. So we have from low to high. High is 3, low is 1. And you can see that in general, we have like good like awareness among the adopters and non-adopters both. On in general, it's 2.5 in the average. So this is good. Now in the impression scale is a little bit opposite. We have really negative impression about the LCT among the adopters and non-adopters both. And I think we have, in the later part, I'll mention that why this, even among the adopters, they have this negative impression. On an average, we have 1.17. That means it's actually moving between highly negative to the somewhat negative. So that means the most of the responses from neutral to the highly negative sides. We really don't have any positive impression scale for the low carbon vehicles. Overall, this 12 we surveyed. The next question we asked to them, Craig, next slide. Like, okay, what are the reasons for LCT adoptions? And there are different reasons came into the interview, but we list in top like main category of 4. The first one is environment. That's one of the main one. And then you have the maintenance and second, and then overall the engine issue and other things. And the last one is the fuel cost. And if we look a little bit more onto the importance of these reasons, we can find that environmental regulation, which is 1.67. And actually that tells a little bit of the things that's why people are adopting. That means if we have the strong environmental regulations, they're more likely to adopt. It's not that they're intentionally adopting it. Actually, that also tells like why they have this negative impression actually, because they're kind of bound to do this kind of things. There are some companies and there are more environmental friendliness, which is 1.17. That means it is still between low to medium in the importance scale. And there is another one which is green public relationship. That means it's like your on brand, like, okay, it's a great green company. That has also some kind of importance. Some companies are more willing to purchase or adopt this LCT if it gives them some kind of green vehicle company or green company. So these are the things from the regions of LCT adoption. The next thing we want to see that, okay, what are the barriers for the LCT adoptions? Again, we list these four, and this is not the whole list. This is not an exhaustive list. You can find more list in our reporting. And the first thing is mainly come into play into the refueling or recharging facilities. Second thing is purchasing cost, and then we have this maintenance and other issue. And the last thing is this technology is not still is unproven. You have the business model is not reliable yet. So these are the things. Now, if we look at the importance scale, you can find that everyone is talking about the lack of refueling and recharging facilities. That one of the main barriers for the LCT adoption. It came into 1.98. That means it's almost in the medium scales. Even if we look into more detail, you can find there are some high importance into that one. And then also the second one is purchasing cost. It came into like many times, and although we put it here purchasing cost, but there are other costs associated with it as well. That means maintenance cost. You have this infrastructure cost as well. And third one is more engine related issue, which is like low range, which is 1.48. So these are the three most important criteria for that's actually hindering companies to adopt the LCT. So the next thing we looked into, okay, if they wants to consider or purchase any vehicles, what are the things they consider? Because that will tell us about the role of the incentives that's play into adoption of any new vehicles. So we asked them that question, and they put this many things, but the most important thing come into play is the operating cost, which is 1.92 on an average value that's come over and over, and then the purchasing cost. And the third one is incentives. That means incentives actually play a good role to adopt a vehicle, especially in this kind of LCT or environment friendly vehicles. So now that means incentive has a role. So now what is the awareness or perceptions, and what is the importance of incentives when they purchase? That's we actually looked into the next one. So next slide we'll talk about that. So the first question was, okay, how do you know about these different types of incentives available? And you can see that in general, actually, I was a little surprised, even among the non-adopters, they are about these kind of incentives. And the scale from 2 to 3, that means most of them actually know about it. On an average, it's 2.167. So even among the non-adopters is 2. So they know about it, but when you go to the impression, this gives a like different results. You can see most of the things are neutral. That means it's mostly like somewhere, could you please go back a little bit? So if you take a look, it's like somewhere between negative to the positive. So there is a good amount, like 50% is saying negative and 50% is positive. I'm not focusing on the positive. I want to know now that why this negative impression is about the incentives. Because in my mind, my hypothesis was incentives is always good. If you give me money, I will buy something because it's free somewhere. But why still people has this negative impression? That's what we want to take a look into next slide. See here we asked them what is the reasons for negative impression. We found different things. But three things come into play. One is the cost ineffective, difficult to acquire, and conditions and restrictions. And you can see that condition and restriction, this is the highest one. Now, if I break down this among the adopters and non-adopters, you can find that even those who actually adopt it, they're not happy about these things. They don't like the restrictions. They're saying that it is cost ineffective and difficult to acquire. That everyone who adopt it, they're saying it. But those who are not adopting it, they are saying, okay, the paperwork is a lot, so I don't want to do these things. And this restriction also hampering them to acquire those kind of things. I think this is a good lesson for when you design incentives, what kind of things we can easily fix. For example, paperwork, I think that's can easily fixed. Waiting period, it could be easily fixed. And difficult to acquire, that's also like there are a lot of process they have to go through. That's really hard, especially from the small fleets, that they don't want to go over these kind of things, because some bigger fleets, larger fleets, they have a specific, maybe some people that are dealing with this. But there's a small fleet, which is a 1 or 2 people's company or 5 people's company. They don't have any specific person who deals with this. So they are really hard to accord this kind of things if there's a lot of paperwork and other things. So this is, I think, a good lessons to learn to how to design an incentives. The next thing we asked about that, okay, if everything is same, then what kind of expectation you have from the government so that you actually will be adopting the low carbon technology? And the things is come, that's the main thing actually they talked about over and over, which is charging infrastructure, which is, you can see the scale is 1.75, that most of the people talk about that. And the second one is more monetary incentives, and third one is collaboration with manufacturers. But if I break down among the adopter and non-adopter, you can see this charging infrastructure support came from the non-adopters most. But from the adopters, you can see that less restrictive environmental regulation they're still talking about, because as I mentioned, environmental regulation was the main reason they adopted. So they're not happy about it, but they adopted it. So that's why they mention it as one of the expected government support, that this is an important one that could play. So these are the findings we got from this about the incentives. The last question we asked them, actually, we try to understand. This is not the question we directly asked, but we try to understand from the analysis that does the awareness of the incentives influence adoption behavior? And we overall found that actually it does. If the companies are more aware of this incentive service, different types of incentives, they will be more likely to adopt this LCT. Even those who are actually currently have, they will be more likely to purchase more. So that's how, at the end, that's our conclusion. That means we have to actually do a lot of educational activities to let people know that, oh, there are incentives are available for kind of. This is always helpful for adopting the LCT. I will end here for now. If you have a question, I will answer later. Thank you, Craig.
Great, thanks, Shuman. Got to move on. We're on a clock here. So next, we're going to turn to the performance evaluation tool, and we're going to call the PET. And we use the results from the tasks that we just discussed to develop a model that forecasts the fuel type evolution of the heavy duty fleet for chosen vocations, drayage, line haul, and construction between 2020 and 2050. So here we see sort of the general design of the PET, going from the inputs at the top through 3 core modules in the middle, down to a set of outputs. So at the top, we have inputs, which are incentives and regulation and their impact on capital and operating expenses, the effect of market innovation on CapEx and OpEx, that's coming from the TRACE model. We have the behavioral factors for technology uptake. We start with a baseline inventory in 2020, sorry. We have characteristics of the vehicles in terms of their VMT, as well as emissions profiles for computing environmental impact. So the PET is structured around a total cost of ownership model that estimates amortized costs of ownership for all fuel technology platforms. We'll talk about that on the next slide. We have a fleet turnover and decision model that simulates how the fleet composition changes over time between 2020 and 2050. That feeds into an emissions model which uses MFAC rates. And the outputs from these flow into an impact model that estimates LCT vehicle uptake, program costs, employment impacts, and emissions outputs and related information. So moving on to the total cost of ownership module is that we show here. This estimates the amortized costs, as I said, of ownership for a variety of vehicle and fuel technologies. At the top, you can see this is a segmented model. We have a model for each region, vehicle class, vehicle technology, fuel, fleet size, and acquisition year. And for each of those characteristics, there are a variety of parameters that we have estimated or taken from literature, acquisition costs, core acquisition costs coming from TRACE and other things, fuel economy as well from TRACE, replacement costs, if applicable, depreciation, registration, et cetera, infrastructure costs in terms of fueling and recharging infrastructure, the costs of fuels, again, coming from TRACE, and then policy coming as a combination of either incentive designs regulations that we want to model or LCFS revenue, that some of that's embedded in the trace model and some of it is represented in the TCO model. And you know, so down in the lower right, you see how we're modeling costs over time for a first owner vehicle life, again, including across all of these domains. Just to go through some of these inputs, we have the regions are essentially the MFAC county air basin air district boundaries, and then we further subdivided those into utility sub areas because yeah, we did electricity price forecasts by utilities in the state. Additional stratification were by fleet size. Why we needed to include fleet sizes there are a number of reasons. One are electricity cost variations. Some utilities give discounts for larger fleets. Incentive designs can consider fleet size and do, like Advanced Clean Fleets. We have the large fleet or priority fleets grouping, as well as regulatory differences. ACF, again, priority fleet categorization there. There may be vehicle technology choice restrictions, as well as mandated retirements by fleet size. So we got fleet size distributions from CARB staff. For drayage, they used Arbor. For our construction and line haul trucks, they use DMV data combined with Dun & Bradstreet to come up with fleet size distributions that, for better or worse, we assumed were fixed throughout. I suspect that might be a dubious assumption, but we had no way of modeling the evolution of fleet size. So I think, as mentioned, we also used annual VMT from the MFAC model in our TCO calculations by vocation. But we noticed, so for a given acquisition year, if we wanted to know what the VMT was for a particular region, we used the VMT estimates from the MFAC forecast for, you know, model year 2025, vehicle purchased in 2025, and looked at what the annual VMT for those would be. We did notice some missing data for some of our vocations, so we decided to smooth that data to get more consistent VMT estimates over time. So just a quick look at lifetime VMT. This is for construction by acquisition year. You can see each line here represents an MFAC region where the thickness of the line is approximately is proportional to population size. The cyan line, the light blue one there, shows the weighted statewide average. The denser regions show higher lifetime VMT per truck. And then just the color coding here, red are the top 3 vehicle population regions. Green are the top 3 for VMT, and blue are the bottom 3. So just to kind of lay that out. We also, in the TCO model, include a technology adjustment factor to represent operational penalties, primarily for battery electric vehicles. The baseline values for these operational penalties that account for, well, we derived it from ANL's work in 2021, and they computed payload capacity losses of approximately 10% for BEVs. So we started with that and assumed that those would improve over time. I think some of these reflect some of the opinions that we saw from the fleets that we interviewed, who actually were operating vehicles in terms of operational limitations. So when we run TCOs through the PET, we get an annualized discounted costs that looks something like this. Here we have for 3 different vocations for battery electric vehicles, the annual costs for each, where each component here is represented in the stacked bar. The red ones primarily are representing vehicle-related costs. We include maintenance and things like that. The purpley ones are infrastructure-related costs, which are pretty small in this. The green are typically our incentives. Well, blue are operations, and the green are incentives. You can see in that first year, the large upfront capital costs with the incentive offset for these battery electric vehicles. The yellow dots represent the net cost for the annual. So anyways, this is just to sort of illustrate what computations are going on in the PET. And then if we look at cumulative costs by ownership year, it looks like this. I guess again, mostly here just to kind of illustrate what's happening, but you can see here in this middle left, how the battery electrics in 2025 are significantly cheaper. That's primarily due to cheaper electricity costs in that year, I think, as well as LCFS credits that are being credited for the electric fleets. Moving on to the fleet turnover model. This models vehicle turnover as a stock and flow system, where annual vehicle stock is modeled by tracking the net annual flows of vehicles into and out of the system. So we start with the 2020 base year, populations, and this is by stratification. And for each of these, we need the growth rate, we need retirements, both loss and through regulatory action, as well as the shares of additions by vehicle age, new or used. And how do we do this? So we get our turnover parameters by looking at historical data in the MFAC fleet database, looking at the net change in vehicle stock by inventory year here in this picture. And so you can see roughly the top 6 years here through age 6, there tend to be a net inflow of trucks, and then so this is net inflow into California. We can't compute exchanges that happen within California. And then for older trucks, we see retirements happening at those. So we assumed that any trucks ages -1 to 1 were new vehicles, and that ages 2 to 6 were used vehicles that were added through net imports to California. Let's see, and then so once we're running through the turnover model and we need to add new trucks, we need to determine the fuel choices that are made for those new truck additions. So the fuel type choices are computed as technology shares using a modified Logit formulation as a function of TCO. This follows a couple of models, a global change analysis model, as well as the tempo model, which has a similar modified Logit formulation that uses, instead of TCO, it uses levelized cost of driving, sort of a normalized VMT normalized driving. So the fuel type choice set in this model, when Q in this representation, it can be restricted by stratification to reflect regulatory constraints. I'll talk about that a little more later. Choice experiment, we followed the GCAM model. Non-cost preferences can be captured by share weights, which I'll talk about those briefly in a sec. We calibrated our share weights to 2020 MFAC fuel type splits through 2020, right? And so here's the share weights that we started with. Future year variations in these share weights were qualitatively determined from both our survey results as well as anticipated impact of regulation and performance. For used trucks, because we do model the addition of used trucks to the fleet as well, we need to keep in mind that we're modeling net changes in used vehicle stock, not total used vehicles, because we don't model used vehicles where the registered vehicle remains in state. So these are coming from outside of state. Our approach is to assume that this distribution is going to match the distribution for some lagged prior period. Thus, if we're adding trucks that are 6 years old, we'll assume the distribution of fuel types for those should match the distribution of fuel types for new trucks that were added to the fleet 6 years prior. This is applied except when regulatory rules restrict used vehicles to particular fuel types. So to connect these model outputs to impacts, so once we run the turnover model, we connect them to the impact model. And so the modules described forecast from 2020 to 2050, the vehicle turnover, including the number of retirements, as well as the number of new and used vehicle purchases. So using those results in the choice model, the vehicles added to the stock are assigned to fuel types, as we just talked about. And then those new vehicle purchases and annual VMT by the various fuel types over time then serve as inputs to the impact model modules, which I'm going to talk about in just a sec. So we have the emissions model again, which just applies based upon our new fuel type splits that we're modeling over time, the MFAC rates associated with those fuel types. These are modeled at the COABDIS region for out through 2020. We're able, you can see in these results the concentration of different fuel types in different areas. Obviously more drayage in the LA basin, a little bit up in the Bay Area, they're showing up here, whereas the line haul spreads out through the Central Valley a little more. Construction is focused on urban areas as we anticipate. So for the impacts module, we modeled the impacts on workforce. And the employment impact is measured on a per unit basis. In other words, the number of full-time equivalent jobs per $1 million invested, or FTE per million. Again, the investments are being modeled as from the output of our turnover model, indicating the number of new vehicles purchased and their cost for each region. They're able to model the investment, and then we used 11 specific investments that derive from those new vehicle purchases, and include the vehicle cost, fuel and electricity costs, maintenance costs, et cetera, as well as two types of infrastructure, both EVSE, electricity supply equipment, charging equipment, and hydrogen refueling. We use the IMPLAN model to model it's an input-output analysis to forecast those expenditures and the associated workforce impacts over time, which is what these are showing. You're seeing up at the top of the investment totals by category, and then the annualized FTEs. The model is implemented in the R language. Data pipelines are coming from a common repository. These are all publicly available data sets or created from intermediate processing like the trace application. Scenario inputs are provided by the analyst through a Shiny interface to execute the model. We also have a scripting interface, which if you're doing a lot of analysis provides, it's a little more useful. The updated version of this, which is coming out this month, will allow you to run a bunch of analysis in the background and then use the Shiny interface to review them without having to run within the Shiny interface. So to this point, we've largely focused on the on-road model. The off-road TCO model was similarly constructed, but efforts to apply a similar kind of fleet turnover approach to the off-road equipment weren't successful due to the sparsity of the equipment bins that we selected. But I'm going to introduce Dr. Canuck Borbunsamson to discuss the TCO model and the associated market parity results. Dr. Borbunsamson is an associate director of the College of Engineering and Center for Environmental Research and Technology, CE-CERT, at the University of California, Riverside. He conducts research in the broad area of sustainable transportation, with a recent focus on decarbonization of medium and heavy-duty vehicles and equipment. So Canuck, I'll hand it over to you.
Right, thank you, Craig, and good afternoon, everyone. So yeah, I have a few slides on off-road equipment analysis and TCO. And first off, just want to talk about the selection of off-road equipment to be included in the analysis. And as you know, off-road equipment types are so broad, so we have to kind of down select to just the ones that have been previously determined to be feasible for electrification or have been demonstrated in the field with zero emission technology. On the slide is the list of equipment type that were selected. Now, for off-road equipment, they are not just varied by type. For each type, there are many sizes that are defined by their horsepower. So we also have to select the proper size for each equipment type as well. So in all, there are a total of 60 combinations of equipment type and size. Next slide, please. The structure of the TCO model is borrowed from the on-road vehicles. But as Craig mentioned, there are many limitations when it comes to off-road equipment data because it's so sparse. So in this project, we were able to only provide statewide estimate only, and we were able to just look at diesel and battery electric technologies. The methodology include the breakdown of TCO into different cost component following the same methodology as the on-road heavy-duty vehicles. When it comes to vehicle costs, because there were not a lot of data points about equipment costs as the whole, we have to break the cost down by components. And for diesel equipment, the main components include engine, fuel tank, and glider. And there is a soft factor, a price markup that we also build in. For battery electric equipment, the components include battery, motor inverter, and glider. For this one, there's also, in addition to the price markup, there's also advanced engineering costs that we assume because of the battery electric equipment being new technology. Next slide, please. I will jump to the results because of the limited time we have. And this is the TCO results for tractor loader backhoe in 100 horsepower bin. So this is medium size on the smaller sides compared to the broad spectrum of this type of equipment. Now, let's focus on the dark blue lines with circle marker. And that is the total cost, total TCO over the life of the equipment, and compare between battery electric and diesel. And we'll see that initially, at least in the next 5 or 10 years, up to 2030, battery electric version is cost competitive to the diesel counterparts. But after that, the TCO for battery electric tractor would go up and exceed that of the diesel tractor. And that's largely driven by the fact that LCFS credit will diminish over time based on the current structure. Next, please. Now, this slide shows the result for the same equipment type, tractor, loader, backhoe, but a smaller one. This one is for the 50 horsepower bin. And again, if we focus on the blue lines in the two figures, we will see that battery electric tractor always have higher TCO as compared to its diesel counterpart. This is true across all the calendar year that we analyze. And this is because for such a small equipment, it doesn't require a lot of energy. Therefore, the fuel cost saving from using electricity and getting LCFS credits are not enough to offset the cost of infrastructure that would be required when the fleet switch to battery electric equipment. Next, please. Now, this is the kind of overview of all the results, all the 60 combinations. If we look at the top left table in 2020, so we see the trend that larger equipment sizes tend to do better. I mean, larger battery electric equipment tend to do better when it comes to TCO comparison with their diesel counterparts. And when it go to 2050, again, those seem to be going away, right? The winning battery electric versions seem to be going away again because of the diminishing LCFS credit. Next slide, please. So in terms of key findings for the off-road equipment TCO, Again, so the incentives are key because without them, then battery electric equipment will have a hard time competing with diesel equivalents. And the infrastructure cost is a big elephant in the room because it's something that new when you switch to the new technology. And for equipment that is small, the added infrastructure cost may be higher than the fuel saving or the energy saving cost that the fleet would get. Now, I'd like to know that there are many assumptions that are made in the analysis because, again, these are very, very new and there's not a lot of cost data that we can use during the study. Thank you, Craig. I will hand it over back to you.
Thanks, Canuck. All right, we're getting short on time, so I'm just going to keep moving really quick so we have some time for questions. So now we're going to turn to the application of the PET for on-road incentive and regulatory analysis. So the first thing we did was compare the PET results to the literature just to provide some grounding. The PET estimates for ZEV vehicles, they tend to correspond well with CARB's estimates for 2025 through 2035. I've compared to the literature here, I've compared to CARB's draft TCO discussion document from 2021, as well as ANL's TCO report from 2021, which were the most recent comprehensive projects that I had for comparison. So we're comparing CARB's report had 2025 through 2035, and ANL had forecasts for the entire range. The PET's TCOs for fuel cell and hydrogen track to CARB's estimates quite well for that 2025 to 2035 range, with ANL's estimates being consistently higher. ANL didn't estimate for natural gas, but the PET and CARB's estimates are in good alignment in 2025, with the PET being more optimistic about the costs in future years. And then finally, for diesel, the PET matches CARB's estimate in 2025, and then kind of splits the estimates between the higher costs of CARB and the lower costs of ANL's estimates. The difference between ANL and CARB's estimates, the fact that ANL's are lower is probably due to ANL's being more of a national model as opposed to CARB's California or our California focus. So we also normalized our TCOs by VMT to compute a sort of a levelized cost of driving and did a comparison on that basis here. The cost components that we compared, because not all of these TCO models include the same things, were CapEx and OpEx, fuel costs, and then the other costs had to be omitted for this comparison. So the first, in each of these charts, the first 3 rows are the PET minimum, middle, and maximums. CARB, we just have one estimate, and then ANL, we have a min and a max, and this is for a 12-year vehicle life. The CARB rows show, yeah, so that's from that document. And then the vertical lines show the kind of highest and lowest range in each group. And broadly speaking, what we see here is that the PET results fall within ANL's ranges in the 25 and 30 for all fuels. But the PET battery electric gets more costly in later years. And why are the PET's battery electric costs higher? It's likely due to electricity cost forecasts, and in particular because this is a population weighted estimate, and PG&E's costs are significantly higher, so it's kind of take up a large portion. So just to look at the fuel cost projections, we forecast, we're showing the relative forecasts of our 3 sources here. Again, the PET forecasts show pretty good consistency with ANL's forecast for hydrogen, with CARB's hydrogen forecast being significantly below both for 2025 before it comes more in line around 2030. The PET's mean electricity rates lie between ANL's lower rates and CARB's higher rates for that 2025 to 35 range. And then the high end of the electricity rates for the PET eventually exceeds CARB's forecast around 2040. assuming that CARB's rates remain flat from 2035 onward. Diesel prices for the PET are pretty close to CARB's for that for what we have data, but again, pretty significantly lower than ANL. So to explore the PET, we conducted a sensitivity analysis across a variety of parameters. This table shows the parameters we varied, which include electricity scenarios, so a range of electricity costs, the vehicle production scenario that comes from the TRACE model, ranging from sort of optimistic costs to conservative costs that are higher. For incentives, just to see the impact of incentives sensitivity wise, we didn't look at a low case, but we had a baseline and a high cost case to compare them. For retail markup, the baseline case was sourced from the ICCT of about 35% for internal combustion vehicles and 40% for ZEVs until 2030, and then matching the matching afterwards. We just varied these for the low and high case just to see what the sensitivity looks like. We had the operations premium that I talked about, so we varied that. Also infrastructure, we varied. We considered a 2-to-1 ratio of supply equipment to trucks. Sorry, that should be reversed. We considered 2 trucks to 1 EVSE as the sort of the baseline, and then varied those for the low and the high case. For vehicle lifetime, we varied those parameters as well as other financing parameters, and then we looked at VMT as well, starting with the MFAC VMT as the baseline, and then scaled that for the high case to match the ANL totals, which were a fair bit higher. So to visualize the impacts of each parameter, we converted the costs into LCOD, as I said, and created tornado charts. These show the levelized cost of driving of the baseline case as the vertical gray line, and the variations caused by varying each of the parameters as horizontal bars to the left and right of the gray line, representing lower and higher levelized costs of driving respectively. Because the change in LCOD can be in the opposite direction of TCO, or else the bars are color-coded by their impact on TCO. So gold is a higher cost, green is lower. And then in each chart, the parameters have been sorted to top to bottom by the widest absolute range of LCOD to clearly identify the parameters that the model is most sensitive to. So just really quickly, in 2025, the parameters impacting VMT are consistently influential. And in all cases, at the top of the charts, we find either VMT targets or vehicle life parameters, which increase VMT as at the top. So generally, as VMT increases, TCO increases and LCOD decreases. This really highlights that fuel costs are a major determining factor for TCO, even when normalized for VMT. That's consistent with what Canuck was just saying about the off-road equipment as well. Sorry, I'm getting some background noise again. So there's a little variation for internal combustion and CNG in the PET model over the parameters we varied that don't impact VMT. Differences in vehicle capital costs related to retail markup have a modest impact. And other than that, those are the primary sort of sensitivities in the model. We also have the drayage results here, but in the interest of time and line haul, I'm just going to move through these. Just a really quick look at how TCOs vary across PET regions. So this is across the state. There's definitely noticeable variations in battery electric costs due to electricity rate differences, but this narrows in the future year distributions. So we did model a range of regulations that we talked about before. The truck and bus regulation is included in the turnover model. We didn't model the manufacturer targets of the advanced clean trucks. We did model advanced clean fleets manufacturer sales mandates as limited choice sets for HDVs starting in 2036. Again, drayage fleet requirements, we modeled those starting in 2024. We partially modeled the priority fleet requirements. I talked about this. We modeled the model year schedule, but not the milestones option. And we didn't model the state and local agency requirements because we weren't including those classes. So this is what it looks like. This is the impact of regulations. So these charts are technology shares by purchase year, for different fleet sizes and for different vocations. Orange is diesel, purple is natural gas, the blue is hydrogen, and the green is battery electric. And so on the right, we see without regulation, and on the left, we see the technology shares with the regulation. So you can clearly see the impact of the regulations for, let's start with drayage. Drayage in the without regulation, we do see some shifting to battery electric, largely, I think, driven early on by our LCFS credits and some operational improvements and incentives. But if we look at the impact of the ACF regulation, then we see that the internal combustion options go away, and we're limited just to the zero emission options, where in this particular scenario, the battery electric is preferred for drayage. You see construction in line haul, the hydrogen being more competitive. There's also variations by fleet size, and you can see the impacts. We do model the fleet size restrictions for construction and line haul also starting in 2024 for the regulation. So to look at incentive designs, we needed some baseline scenarios based upon our sensitivity analysis. We chose the following scenarios to consider: an optimistic, a mid, and a conservative scenario. These are the parameters that we chose for those. The mid-market scenario generally corresponds with the sensitivity base case, except that we did adopt that 2-to-1 truck to EVSE ratio based upon some analysis that one of our GSRs did on drayage operations data. So for incentive design, we considered two parameters, both the incentive amounts available in a given year by vocation and fleet size, and whether or not incentive caps, that is a cap on whether incentives can exceed the differential cost of the conventional diesel truck and the alternative fuel or low carbon fuel vehicle. Within this, for incentive amounts, we chose 4 different sort of designs. One is the tapering 2035, where we started with current HVIP incentive rates and gradually reduced them between 2025 and 2035 to 0. The second is a tapering design that goes out to 2050, the same sort of approach. A flat design just holds them stable indefinitely through 2050, and then a no incentive design as sort of a base case for comparison. And then we have the incentive caps either with or without. So here we're showing incentive costs by vocation. So we run the model, we turn over a model, we get for a given design, it produces these results for new truck purchases and associated incentives. Here we're showing the distribution of incentive costs over time by fuel type for the mid-market scenario using the 2035 tapering design. So these are the values that go into our assessment of different designs. And so what we did is for each of these designs, we ran the model, we computed what the incentive costs were, we computed the emissions outputs, and we used the cost effectiveness ratio that we identified previously from CMAQ analysis to score the different combinations of incentive designs across different market scenarios. Here, the colors are sort of groupings of market scenarios. And if we look at the top for each color, we see that the tapering 2035 design with caps is the preferred solution. There's a little more in the report about how we did this analysis, but broadly, that's how we came up with this selection recommendation that CARB should gradually reduce incentives out to 2035 when they're removed completely and regulations take full force. So looking at market parity under this design, The battery electric vehicles generally meet or exceed parity in the mid and optimistic cases out through 2025, though there are some vocational differences here, but generally the BEVs perform well. Fuel cell electrics are the preferred ZEV option in the conservative case, though they lose parity without incentive supports. I think these results are somewhat similar to, again, what we saw on the off-road side. So this is just a look at the technology shares for the capped tapering design mid-market, and kind of already talked a bit about this, where you can see the regulatory onsets. And again, for the different scenarios here. So this is the optimistic. You can see there's not much difference in the splits between the mid-market and the optimistic scenario. But as we get into the conservative market, we see that the fuel cell, the conservative market assumptions, which includes higher electricity costs, we see that the fuel cell vehicles become the preferred choice when the ICE vehicles can't be used. So these plots show new vehicle purchases over time. The vertical lines show regulatory onset, the ACF, and here the 2035 discontinuity is induced by Advanced Clean Fleets regulatory requirements. The PET doesn't model supply side, and it doesn't model strategic decisions by fleets. So in the real world, we might see sort of fleets anticipating sort of doomsday, sort of drop dead for their vehicles earlier, and that transition starting a little sooner, so you don't see that kind of crazy spike in 2035. OEMs will also anticipate this spike and may market to mitigate that. And continuing education for fleets would be important to avoid sort of doomsday. This is just a look, kind of the same thing, but instead of new vehicle purchases, it's total fleet population by technology. You can see, and then also by vocation, and you can see the model is showing regulatory compliance for drayage by 2035, and that transition pushing out into 2050 for line haul and construction. Okay, so the last couple of slides here, this is a little bit complicated, but the trace model has its own forecast of vehicle splits that it uses to compute vehicle costs on the basis of volumes of components produced. And we are modeling, but we're modeling our own transition. So the trace model is an optimization. Ours is a demand side model that tries to model what fleets are going to do. Ideally, on the back end, the PET model and the trace model should be relatively close. So if we look here, we're comparing the left columns are the PET model and the trace model, the right columns are the trace model. You see in 2020, they're nearly identical. And then as we move out, and these are VMT splits by fuel type, as we move out, you start to see some deviations. So this is the mid base case, so the sort of the middle case. Trace models a more significant role for natural gas trucks, particularly in the construction and line haul vocations. This indicates, I think, that the system cost advantages targeted by trace differ a little bit from the fleet cost focused dynamics of the PET. Generally, PET is slower to transition away from diesel in all cases, but for all three market penetration scenarios, the share of ICE vehicles tends to track closely between the models for construction and line haul trucks through at least 2035.
Craig, I'm sorry to interrupt. We're at time, so I was hoping we could maybe.
Yep, I will wrap up.
Okay.
I was just going to say, sorry, I was trying. When we look at the conservative case, you see things get in much better alignment, particularly as you look at it 2045 and 2050 for the splits between battery electric and fuel cell electric vehicles. I had some concluding remarks. I think maybe we should just open it up to questions, unless you want me to go through these. apologies for going along. This was a big project with a lot of content that we wanted to be able to get in front of you today. Please see the report, and yeah, we'd absolutely appreciate questions.
Maybe you can leave it on the concluding remarks slide as we start to
Yep.
field questions.
The one question I see in the Q&A is a question about whether presentations are available, and you answered that one. So.
Yes, yes, it'll be, we'll make it ADA compliant, and then we'll put it on the website when that's ready. The link is in the chat for the website for this project. There's also a question from Rose Zoki, sorry if I'm mispronouncing your last name, on PM10, whether it's weighted by 20 as with the Carl Moyer program.
So,
That was earlier, that was referring to a much earlier slide.
Yeah, I'm sorry, could you repeat that?
PM10 is not weighted by 20 as with the Moyer program. That's the text.
Okay, thank you for that. We I believe that we did not use the 20 weighting in our analysis. I'd need to go back and confirm that. We looked at both of them, but I think we did not use the PM10 20 weight.
Great, thank you. Are there any, people are free to use the raised hand feature? All right, I see a question from Jacqueline Moore. Jacqueline, go ahead and unmute yourself.
Hi there, Jacqueline Moore from PMSA. I wanted to thank the universities and all the presenters today for very detailed presentation. I did have one question. I did not see any analysis on hydrogen ice technologies, and I was wondering what was the reasoning for that? Why wasn't that modeled along with like CNG ice and then some of the other technologies that were included?
Yeah, so I'll respond to that and then maybe ask Blake to also chime in on that. I think when we looked at the market, we didn't see a lot of hydrogen ice technology either available or under consideration, under significant consideration. I recognize that it's kind of an open market right now. And things may evolve. Blake, in your work on the trace model, did you consider hydrogen ice vehicles at all? And if so, was there a reason to omit them?
Yeah, great question. Similar thoughts to Craig. I think certainly these were considered. I think we see ICE hydrogen vehicles considered outside the US a lot as well, particularly in Europe. From our perspective, the range limitation was pretty severe. It's great to have hydrogen from a greenhouse gas position, but you still have potentially the NOx emissions that need to be worked out. And then also the efficiency, right? With an ICE internal combustion engine, much less efficient than a fuel cell, the range issues are somewhat constraining.
Thank you for that.
Sorry.
No, I was just going to say thank you for that. So I represent the maritime space and for cargo handling equipment, especially for certain, heavy lifts like top handlers and so forth for very particular applications. We think hydrogen ice may be the answer, maybe in the interim, maybe not. But we think that's an important consideration to include here for for this analysis, and this is for low carbon transportation, and we recognize there are de minimis NOx emissions that go along with this, but for greenhouse gases in particular, I think it's a perfect technology for certain applications. So I'm not sure we can keep this in consideration for this analysis or future, but it is a technology that is under consideration.
Yeah, I'll just one quick response. Thanks again for your question. The model is certainly capable of representing additional fuel type and fuel technology drivetrains. Adding it would largely, well, there's a couple of complications, right? Our choice model is pretty coarse as well, and so being able to distinguish between two hydrogen fuel trains. There would be cost considerations associated with that. And then we also need emissions factors to be able to incorporate that into the model. And I'm not aware of impact modeling H2 emissions, so we need sort of custom emissions rates for that. But the framework certainly could handle it, so we definitely be open to including it if there was a need for it.
Okay, thank you there. Yeah, if you know, there's an appetite for expanding that analysis, I think we'd be very much supportive and can put you in touch with some of the manufacturers that are you know, undergoing manufacturing and or excuse me, demonstrations rather, and doing some of those emissions tests. So thank you, Craig. Really appreciate it.
Thanks.
Okay, there's a question in the chat from Jesse Denver of GoBiz. Did the research team connect with CalSTART and/or GNA, who are administrating incentive programs and working directly with a significant number of fleets, plus have experience with the data to inform the behavior analysis?
We did collaborate with CalSTART. In particular, we received a lot of data from CARB staff that came from CalSTART in part, I believe. We also collaborated with CalSTART on using their InfoShed tool, which is well, at the start of the project, it was thought that the InfoShed tool would be providing a lot of direct data that we could use. But the InfoShed tool is a tool it's a well-designed tool for capturing the results of pilots, detailed cost information from pilots of zero-emission technologies being deployed. But we found that it's really sort of one more TRL 6 sort of deployments as opposed to the 7 to 9 that we were looking at. So we did collaborate. The behavioral analysis, I will admit, was frustrating. There is broadly a lack of quality data on fleet behavior under the presence of incentives. And I did mention in our presentation that we do have research going on by Dr. Young-In Bae. She's just about to complete it, where she did run online choice experiments targeting fleets, providing them with alternative fuel choice scenarios to select from. And so she's collected that data and is working on completing that model and producing results. And we expect that to come out soon. We see that as a potential to drop in for at least a portion. I think that focused primarily on drayage, but I'd have to have Young-In elaborate on that. But we see that as a model that can fit directly into the framework as a replacement for the modified logit that we're currently using. But there is a lot of work that can be done on the choice model and the broader behavioral analysis, particularly as incentive or as zero emission deployment matures and we get better information on how fleets are responding to the market.
All right, are there any other questions? You can use the raised hand feature if you'd like to say your question out loud, or you can put it in the chat. All right, I'm not seeing any additional questions. I want to start by thanking Professor Ritchie for being the principal investigator on this project, and also Dr. Rind for coordinating this massive project. I want to also thank Drs. Buribumsomsin, Lane, and Mitra for presenting along with Craig today. And just the whole team did a phenomenal job on a very complicated project, huge and complicated project. I also want to thank all of the CARB staff that helped with this and came to a lot of the discussions and were very engaged in helping to provide advice and recommendations to the team. With that, Craig, do you have any closing remarks, or Professor Ritchie?
I just want to echo what you just said. This project, we appreciate the extended input and engagement of CARB staff, who were incredibly helpful in shaping the research and I think making it a success. Appreciate the patience of CARB. We ran long on this project. It was complicated, but CARB staff were great in working with us to completion. So thank you so much to everybody involved, as well as the project team. Thank you.
Yeah, Sonia, I
Great.
just wanted to echo Craig's comments. Appreciate all the support and your leadership on this really complex project, but really satisfying and exciting one to complete.
Thank you so much, Professor Ritchie. All right, just as a final reminder, CARB does provide the final report and the slides and the recording of this video online on the contract page. I provided the link in the chat. We do have to make all of our documents ADA compliant so that they're accessible to anyone and everyone. That does take some time, so please be patient as we get those ready. So yeah, the report and the slides and this recording will be available on the website as soon as we can manage it. Thank you, everyone. Sorry we went over by 12 minutes. We really appreciate your time and attention on a Friday afternoon. Thank you so much and have a great rest of your evening.
Thanks, everybody. Bye.